next speaker is going to be talking about how AI powered robots are building a more resilient future. Of course, the best person to speak about this subject is Mr. Sebastien De Halleux. He is a co-founder and chief gaming officer at Matchday, and he'll be talking about AI robots and their future. Ladies and gentlemen, big round of applause, please.
Hi, everyone. I'm absolutely thrilled to be back in beautiful Yerevan, a city I've had the chance to visit not once, but twice in the past 2 months. And if my clicker cooperates, we'll get started to talk about robots. Can this work? There we go. So I'm here today to really talk about robots and their role in building a more resilient future on our planet. Robots like this humanoid behind me, but also robots like this wind-powered marine robot, and this autonomous off-road robot, and also this quadruped robot, robots of all shapes and sizes. But in fact, my real focus will be on talking about the cutting edge of embodied AI, the transformative enabler that enables the latest advance in robot brains. But first, let's take a step back. Look behind you. This is Saturn. And pause a second, because this is one of the most extraordinary selfies ever taken in the history of humanity. You can see our little planet there from 900 million miles away, a shot taken by the Cassini probe as it rounded Saturn. So let's zoom on this little blue dot. This planet we call Earth, ironically, is 70% water. And oceans drive key systems that affect humanity, no matter how remote they seem. Systems like global weather, coastal land use, energy supplies, and of course, global logistics, because we should not forget that many objects we use daily come to us via an ocean-going container ship. 30% of Earth is covered by land, and we like to cluster in dense parts of this land that we call cities. And overall, we only inhabit about 10% of the total landmass. But all is not well on planet Earth. Resources that we once thought as unlimited are being depleted. All over the world, land is unsustainably exploited for food production, deforested rapidly. Soils are drained of nutrients in our quest to feed our growing species. And in oceans, too, are unsustainably exploited for food. Take global fish stock, for example. For millions of years, global fish captures have increased until 1996, when we've reached peak fisheries, and they've been flat ever since. Floods from extreme weathers are on the rise, and not another day passes by without another catastrophic example, more and more every year. And fires from extreme weather are also on the rise, fueled by extreme droughts with extremely terrifying consequences. The destructive powers of storm and hurricanes are increasing as they feed from increased amount of heat from the ocean, forcing us to constantly rebuild our infrastructure. In fact, the Stockholm-based Global Resilience Institute has published the results of their latest survey, and they estimate that we are currently breaching 6 of the 9 named planetary boundaries: biogeochemical flows, freshwater and land system changes, biosphere integrity, climate change, and what they call novel entities. Think plastic in the ocean, sadly. If you came home with a report card like this, you'd be in trouble. But there's also some good news. So I just want to repeat those here very briefly, because we all know, for starters, that we need a lot of energy to continue our growth. And the good news is there's no shortage of it. In fact, every 1.5 hours, we get enough energy from the nearby star to fulfill the entire current worldwide consumption from all sources on the planet. About 480 exajoules versus 430. And we are becoming better at capturing and delivering this energy to fuel our growth. In fact, solar energy, whether it's in radiation form or in wind form, is becoming cheaper than fossil fuels for the first time in history. It has experienced an almost 10 times decline in pricing over the past decade. In addition, renewable energy, we are becoming better at storing it, thanks to breakthroughs in battery chemistries and material sciences. Think, for example, that the car batteries, lead acid from the 1970s, could store about 50 watt-hours per kilogram. And the upcoming solid-state lithium metal batteries promise to deliver about 500 watt-hours per kilogram, another 10x increase in capacity. So thanks to our nearby star, the sun, we have ample energy and ever-improving means to capture it and store it. And so we're really living through an amazing planet-scale energy transition. And the robots are going to be key beneficiaries of this. The scale of this transformation is absolutely epic. Wherever you look in Yerevan and beyond, there are construction sites as we adapt our infrastructure and densify the land use for inhabitable areas. And as we move our energy generation, solar is moving to deserts, and wind energy in many places around the world is moving offshore in remote areas. And of course, deep underground, all this renewable energy infrastructure requires us to extract more minerals and significantly increasing the mining capacity worldwide. So let's pause here and ask ourselves, who will help build all of this? Who will help maintain this infrastructure, especially in remote areas? Given the size and the complexity of this global infrastructure and the size of our planet, we need some help. And also, it's worth remembering that much of activity on the planet remains unknown. And so I would argue that one of the first missions for robots is one that we would call the quantified planet. Because after all, we cannot fix what we cannot measure, as the saying goes. So take a cube of oceans, for example. As the sun radiates, we can measure solar radiation to understand how much of that energy is absorbed by the ocean and how much of it bounces back straight into space. Because this heat through evaporation is going to create clouds and eventually precipitation, so rain and snow over land. And the wind, the surface wind, will carry that moisture and will carry it ultimately over us and will be responsible for the snows on top of the mountains. But some of that energy is going to go deep into layers in the ocean, like a giant planetary boiler, a phenomenon that we like to call global warming. And we can measure that through thermal profiles. And there are currents mixing this heat in the ocean, which we can also measure. Of course, we need to measure the surface currents, the most famous of which is the Gulf Stream. Why? Because they take the heat from the tropics to the pole with melting consequences. And of course, we know very little about the shape of the floor below the ocean. And it's home to very large mountain range, active volcanoes, deep canyons, etc. And let's not forget that oceans is the largest biome on the planet by volume, and we know very little about the species that live there. So this quantification mission was the genesis of a robot called the Saildrone Explorer, which is a 7-meter-long, bright orange robot, which is technically called an uncrewed surface vehicle, or USV. And each combines wind power propulsion with solar-powered sensors and communication, which enable them to perform long-range autonomous missions in the harshest ocean environment on the planet. Now, the thing that's funny is that Saildrone's patented wind propulsion system was the result of 10 years of R&D in the pursuit of the land speed record in the land yacht in deserts around the world. Sometimes ironic how a desert pursuit can lead through an innovation in ocean propulsion. So how does it work? Well, think of an airplane on the top and a Saildrone at the bottom. And each drone, the propulsion systems consist of this tall wing with a longitudinal spar and a vertical tail with a trim tab that adjusts the angle of the wing to the wind, just like the elevator trim tab on a plane adjusts the pitch of the plane. And this is combined with a rudder for steerage, and the whole system only uses 3 watts of power, and is enough to send a robot across oceans around the world. So the result is a robot that uses no crew, no fuel, no maintenance at sea, no emissions, and makes no noise. It's an amazing robot. But what's the really amazing part is what's inside. These robots are packed with sensors that measure atmospheric variables like wind strength, direction, pressure, humidity, etc., but also underwater measurements like salinity, water temperature, dissolved CO2, and even deeper using acoustics, counting fish with sonars and mapping the bottom of the sea. And all this data is transmitted in real time from the robots to researchers, to the clients, and to computer models over satellite. So above the surface, I'll give you one example. We have onboard cameras that have accrued a very large data set of tagged images, which we like to think as the ImageNet of the oceans. And this unique data set has enabled us to train the first marine AI that's capable of full maritime domain awareness, where everything is always moving all the time in every frame. Now, most of the time, you just see sky and water, but can you count how many birds there are in this picture, or how many ships? Well, Saildrone Intelligence can, with superhuman capability over millions of images. And this helps monitor traffic in sensitive areas, detect illegal fishing, and generally keep an eye on what's happening in the high seas, which is not regulated. It's a task very different for humans on a transient vessel, especially as the people doing illegal activities tend to turn the lights off and turn the AIS signal off. Can you see them? Here they are, in the yellow boxes. Monitoring everything that either sails on the surface or flies in the air over 70% of the planet is an ideal job for a fleet of robots. They never get tired and they are super accurate. But let's admit it, sometimes they encounter novel situations they've never seen before, and so they hesitate around what that is. Or sometimes the algorithm just gets tricked because there are seal-riding robots high up in the Arctic that it labels as someone. We push these robots really, really hard. So we push them to the edge of the world. Every year, we send them to the Arctic to measure the rate at which the ice is melting and to monitor other sort of climate-important factors. This is a very, very tough environment. It looks like another planet. Or we send them in the south, around Antarctica, where they completed recently the first unmanned navigation, the first robots to go around the planet unaided. Exactly 120 years after us humans first wintered in Antarctica on a ship, sailing ship called the Belgica. So monitoring data from this mission really played a key role in better understanding the Southern Ocean in its role in monitoring, in regulating carbon dioxide. Saildrone data showed for the very first time that the Southern Ocean in winter is actually outgassing CO2, releasing CO2, whereas the previous scientific hypothesis was the Southern Ocean was a carbon sink. And so these kind of big discoveries are really important for us to better understand how we model the future impact of climate change. And as our design became more robust and our robots got more miles under their hulls, we started tackling more complex problems, like hurricane tracking. This is a very large area of the Atlantic to monitor. And we do this now routinely. But our first success was in 2021 with Hurricane Sam. And the Saildrone was in that little white box there, in the eye of the hurricane. So I hope you had a good lunch, because this is how it feels. No one had ever seen this footage before and lived to tell the tale. This is the inside of a Category 4 hurricane at sea. Waves over 46 feet high. Winds over 100 miles per hour. It's absolutely harrowing, and no humans would ever be seen there. But robots, it's a job for robots. As a matter of fact, this robotic tale was recently covered by the New York Times in this beautiful illustrated story, which I strongly encourage you to check out. But if you now dip below the surface, you get into a completely new world. It's like an alien planet. And we know very little of it. It's 300 million square kilometers that we know very little about. Actually, we haven't mapped 80% of the ocean. We have no clue what's going there. So when you're faced with such a gigantic challenge, you need a proper big tool to do this. And so we built a gigantic robot called the Saildrone Surveyor, which is 72 feet long. That's carrying a 1-ton sonar, and that's capable to image the bottom of the sea down to 8,000 meters. That's 24,000 feet. And this robot can autonomously map any part of the ocean with zero emission. And that led us to join an effort called WCIT2024, which is a human endeavor trying to map all of the ocean floor by 2030, started in Japan. And as we started these endeavors, the robot is getting us a lot of data, and we're discovering amazing things, brand new chains of mountains that no one even knew existed, and also shipwrecks that have never been discovered. And as you make the sea transparent, did you know that there's around 300,000 shipwrecks from every single era of humanity waiting to be discovered? I'm very excited about this project. But of course, our goal was not to build one robot, it was to build a fleet of 1,000 robots to achieve planetary coverage at a 6 by 6 degree resolution. So if you break down the ocean in little square, 360 nautical miles square, you get 1,000 robots that could cover 300 million square kilometers of ocean. Now, easier said than done, and building a large-scale manufacturing of robots like this is really hard, and we learned a lot about designing for scale. But not just the robots themselves, delivering the data at scale from those robots to where it matters in real time with quality control was very complex. Because this is the most important part. At the end of the day, better input into a model leads to better output. So this is really the role that these robots perform. Outputs like capturing El Nino and better understanding these phenomena. But over time, sail drones combined with data from satellites and buoys and ships have become an integral part of an enabler of the quantified planet. And in a rapidly changing climate, this efficient delivery of data, spatially and temporally, is really key to understand what we are about to face. Because after all, we humans, we can only prepare for what we can predict. And computing, packaging, and delivering all of this data and these computations into the hands of everyone was an effort that we did through our Sail Drone Forecast app that any of you can download to ensure that the output of these robots benefits everyone on Earth. So, as the planet gets quantified, the real question is, what do you do about it? Well, on land, the answer is to increase the resiliency of our infrastructure, our houses, our buildings, our schools, our hospitals, our airports, etc. And so in practical terms, this means construction. Lots and lots and lots of construction. As a matter of fact, we build, but very little has changed in the way we build for the past 100 years. And did you know that construction utilizes 50% of all our non-renewable resource that we consume? It's really mind-boggling when you think about it. But just look up at the building around you. Each building is made up of millions of decisions because these resources are assembled into complex, dynamic projects, and each construction stage doesn't always go according to plan. So you have to constantly adapt this to the changing condition. No wonder why the majority of building projects are late and over budget, and so often really drastically so. So there is a new class of robot tackling this problem that I want to talk to you about. Autonomous machines that are designed to walk around and monitor complex construction sites in real time. Imagine for a second a world where you could see the world through a mirror that is in silicon with millimeter accuracy, where every component of the building is scanned, is measured, is labeled, and then is compared to a digital blueprint. The mistakes are caught in real time, and you can remedy them very early, and so that has a huge impact on your budget and your timeline. And of course, you have to do this without extra workforce because we're already in a deep shortage in the labor force. Now, these robots exist, and I want to tell you about how they came to be because it's a very interesting story. It started in outer space, on Mars specifically, where some members of our team worked on the Mars helicopter. While many people are familiar with the rovers, Perseverance and Opportunity, less of us are familiar with the first helicopter to fly on another planet called Ingenuity. Now, unlike its rover companions, which were remote control, you cannot remote control a helicopter because of the latency in the communication. So this was a fully autonomous robot. It was designed to fly maybe 5 times over 30 days, but actually it flew 72 times over 3 years, higher and faster than anyone has ever imagined. So building on this concept of a fully autonomous robot, our team decided to take the know-how about operating an autonomous robot without GPS, maps, or communication to Earth, and went deep underground into caves and mines. And this was part of a DARPA-initiated subterranean challenge. No GPS, no map, no communication, just a robot with its own edge compute. And when you look at these robots, flying completely autonomous, it's just mesmerizing because they're fulfilling the exploratory mission without any human input, deciding where to go and how to complete their mission. Now, what's really cool about caves is that they all work together as a team. Big wheeled robots with lots of compute and heavy robots would just go down in those caves and mines until they reach a point where the ground was not flat enough, and then they unleashed the quadruped robot that would tackle more complex terrain, all while the flying robots would map the complex vertical shafts and hard-to-reach area. But what they all did is that they shared their data and created digital twins of these caves. So one robot goes and explores one tunnel, captures data, and they see reality through their cameras and LiDARs and understand the space digitally. And then they meet up with other robots exploring other tunnels. And then they unify it in a single data product, which is a digital twin of the cave system that they're exploring. So if a cave is a natural environment, it was the ideal testing ground to tackle those robot construction site problems. Dark, dangerous, always changing, often with no communication. There are many similarities between a construction site and a cave or a mine underground. Most importantly, each robot is not given instructions. They're not remote controlled. They're given a high-level mission, like go build this digital twin, and off the robot goes. Using their own sensors and onboard AI, they decide how to best fulfill the mission in an environment it has never seen before, that's constantly changing. So it explores the building, and it explores every room, nook and cranny. It avoids the obstacles. You know, sometimes it's a wall that was not there yesterday. And they avoid workers, humans who are moving around, and other activity on site. And methodically, the robot that knows nothing about the building covers the entirety of the construction site and increases its coverage and the resolution of the scan. So the resulting digital twin is a true mirror image of the world. But it's not a photograph. It is a 3D point cloud where every point is placed with millimeter precision, describing how the building looked at that precise moment in time. And with this, the robots are able to do magical things, like calculate all the deviations in a building construction in real time, comparing the blueprint, which is on the left, with reality on the right, clearly showing where all the deviations are, like that missing door frame in pink. It's really magical stuff. So how is this magic happening? It's all happening in the robot AI brain. So let me just walk you through how that works. So first, the robot captures sensory inputs from the physical world it lives in. So we're talking about cameras and LiDAR for vision, force feedback in terms of its limbs, gas detector from the air, and even listening to natural language commands or feedback from people around it. Now, this data is very complex, and it's very unique. And you don't find it on the internet, like text and images that are being used to train the LLMs that we've been discussing all day long. Such data really does not exist in the wild. You have to go and collect it yourself. You really need to actually operate real robots in the real world after you've done all your simulation, and this was the really big key to our success. So the more you are in the actual field, the more you collect training data, the more you can feed the AI model, which becomes better and better in a kind of a virtuous loop of learning. But the trick is you can only release the robot in the field if it's safe, because you do not want to injure anyone while collecting this data. You know, imagine like, you know, the regular AI models we're all familiar with can tell you that this is a cat with like 95% certainty. But if you are a construction robot and you're approaching the edge of the 35th floor of a skyscraper, you don't want to have a 95% certainty that there's an edge here. You want to make sure you don't fall off and injure someone. So the robot brain, we actually call it a field foundation model, or FFM. Just like the large language model that power the AI chats, they shine by their generalizability. They can deal with new conditions. But unlike the LLMs, the large language models, they are anchored in the principle of physical safety. Just think of these things as two halves of the brain, you know, combining safety in your current condition with generalizability in new conditions, all of which has to happen on the robot edge because there is no communication. So first, the sensory input we discussed are used to solve classical problems in robotics, problems like localization, mapping, and planning. But we don't do this in a deterministic way. We do this in a probabilistic way. So this is solving all the equation at each intersection of these domains. Where am I? Probabilistically. What does my environment look like? Probabilistically. And where could I go to fulfill my mission? So this results in robots doing things like frontier exploration, which is a strategy where the robot performs autonomous navigation in an unknown environment. It explores these frontiers, and then the segments between the explored area and the unexplored region, which is the frontier. And then by moving to each frontier, it makes sure that it covers the whole building without any human input. Of course, that would be too easy if there was not a lot of obstacles, so it uses semantic and all kinds of different techniques to recognize obstacles and to route the path around them. The obstacles are here in red. And the output of these calculation is a sort of probabilistic understanding of the world, which we call belief space. And there are many, many dimensions in which robots can understand the world. Some might be the spatial structure of the world, some might be the geometric, sort of shape of the world, some might be the risk, some might be communication. There are many, many different ways that the robot is calculating probabilistic visions of the world called belief space. So these robots then develop this internal representation in their own mind of what the world is probably looking like. This is a geometric belief space, for example. And by combining dozens of those belief spaces, you can use the robot in the field safely, with safe operation. And this is, of course, when the magic of large models comes in. So this is the large model part of the FFM, which help to generalize the mission planning based on the sensory input and those belief space that the robot has constructed autonomously. And these models, unlike the large LLMs, have to be super efficient because they run on a local GPU on the robot, which is powered by a battery. There's no internet connection here. And that enables a single robot to autonomously navigate and map multi-story, million square feet type projects with no prior ID, map, GPS, or internet connection, and it's focusing on its mission to build a digital twin of the whole structure. And the final step is to take the output of the large model and extract a map of the risk and rewards as the robot understands them. So this is, like how the robot thinks of the world, and it looks, at some areas that are better known and some areas that are less known, and it wants to probe those areas. So, for example, am I safe to drive over this bush? Will it compress under my weight, or can I not drive, against this tree trunk that will be stronger than me? So, in summary, what goes on into a robot mind at the leading edge of those FFM are really two things. The safety part, which is the probabilistic function of robotics that lead into the creation of these probabilistic belief spaces and that ensures safe operation. And then the generalizability part, which is the large model that takes those inputs and create risk-reward features of the world around them. And the fun part is that, the FFM actually does not care what the robot looks like in terms of embodiment, because the mission, the high-level mission plan, is only translated into the commands for the limbs at the very late stage. Whether it's move that propeller, or turn that wheel, or actuate that limb, the robot doesn't really care, or the FFM doesn't really care. And this is why I've shown you so many different types of robots at work. FFM are embodiment agnostic. They were equally well on humanoids, and which are promising form factor, as was said previously, because much of the world was built for the human body shape. But as always, if there is a special type of job, there is a special type of robot. A humanoid, it's great at traversing complex terrain. It has eyesight at human level. It's a really nice attribute. But if you want to go really far, very fast, it's hard to beat wheels, for example. And if you really need complex terrain stability and versatility, quadrupeds are an ideal form factor. And so all of these robots are powered by the same development in embodied AI, which at our company, Field AI, we call field foundation models, and they have been deployed around hundreds of sites globally on every single continent. And as the robots continue to build those digital twins of the physical world, they make construction process go faster, better, and cheaper, like monitoring these existing industrial plants, energy generation sites, and many other critical infrastructure, making them more resilient. This is really the role that the robots do. But we've been on land, so if you just look up for a second, also in the air there are robots that use the AI-powered brain to bring this resiliency. To do things like warehouse-to-warehouse aerial delivery using autonomous flying drones, as Mightyfly is doing in California, or carrying people over coastal water in ground-effect electric vehicles that fly at very low altitude, a feat that's been accomplished by Regent Craft on the East Coast. And if you go all the way to space, Clear Space in Switzerland is using autonomous robot to remove space junk from valuable orbit. So as we reflect upon these AI-powered robots and what they are doing for us in terms of improving the resiliency of our planet, it's quite clear that my talk title is wrong. I shouldn't have said the robots are coming. I should really have said the robots are already here. Thank you.